Here we are looking at the fundamental group of a surface.
Groups. Informally, a group is a set with a way to add and subtract things. More precisely, a group is a set G with a binary operation, like addition or multiplication, such that if we perform that operation with two elements in the set, we get another element in the set. Here are some following properties of groups, and for these examples, we'll be using addition as the binary operator. For any A, B, C element G, A plus B plus C equals A plus B plus C, which is the associative property. The second property is that identity property. There is some E of G such that E plus A equals A plus E, which is equal to A for all A of element G, and for addition, the element is 0. The third property is for any A element G, there's some negative A element G such that A plus negative A equals negative A plus A equals E, which is the inverse property. Note that it's not necessary for A plus B equals B plus A, so the groups do not have to be commutative.
Now we will look at some examples of groups. The set E is a group with addition defined as E plus E equals to E. In this case, E is the identity. The set Z is a group with addition defined as normal addition. The identity is 0 and the inverse of A is minus A. The set Z follows the arithmetic of addition and multiplication. The set Z-square is a group with addition defined pointwise. The identity is 0, 0 and the inverse of A, B is minus A minus B. Z-square is just the x coordinates and the y coordinates.
Okay, so now we're going to talk about loops. Consider a random surface. We'll use this torus as an example. We're going to choose a point on that surface. What the point is doesn't matter, any point will do. We'll choose this black one here. Now we're going to draw loops that start and end at that point. For example, in red, should be in red, this loop here is a loop that starts at a black point and ends at a black point. We could also have a loop going all the way around the hole and one going around the circumference, quote unquote, circumference of a torus, or one of the circumferences. Now we're going to say that the two loops are the same. We're going to form one onto another. A good analogy for this is thinking of the loops as a rubber band. Considering this black loop here and this second black loop, if you think of the inner smaller one as a rubber band, it's pretty easy to see you can kind of stretch it out to get to the bigger one. So we're going to say that those two loops are the same. It's also true that the black loop, either of them, because they're the same, and either of the red loops are actually not the same. If you think of it as a rubber band, you can try sliding it around. You won't be able to transform one of the loops into another. Now we're going to add two loops by concatenating them. Basically, concatenation, which works better for paths, is you would just take two loops or paths and you combine the end of the first one with the start of the second one. Then that's how you get the concatenation of the two paths, which is this red one here. Similarly, we're going to do that for loops, which is just a little messier, but it's the same concept. You draw two loops, you combine the end of the first loop or with the start of the second loop. That'll give you some third loop that we're going to find to be their sum. Now, using these concepts, we define the fundamental group to be the set of loops up to deformation, which basically means using our form of equivalence by stretching it like a rubber band to get a second one, with addition defined as on the last slide, which is basically concatenation.
The fundamental group of a sphere. So the fundamental group of a sphere is actually the identity. This is because if we take a point on this, an arbitrary point on the sphere, and make a loop around it, we can actually cover the whole sphere by stretching this loop out until it goes behind and around the sphere, then back to the other side of the original loop. The fundamental group of a torus is the integers in the second dimension. So there are a couple ways we can draw loops on this torus. One way is to go around the surface like this, and another way is to go behind, under, and back up at the same point. And this will be the starting and ending point for both loops. We can count the loops, the amount of loops in this group as two integer coordinates a and b. It can be found by the number of counterclockwise loops on the surface, and the inverse of that would be the number of clockwise loops on the surface. The same thing is true for b, where the counterclockwise loops are positive and the clockwise loops are the inverse of that. The fundamental group of the real number system in the second dimension, excluding the origin, is the integers. This is because there's only one way to draw a loop around the origin that ends up at the same point. And by doing this multiple times, you can actually cover the whole space.
Now consider some applications of fundamental groups. In particular, if you can morph one object onto another, then they have the same fundamental group. Note that having the same fundamental group does not imply morphisms both ways. That means that if you have two objects O and P and they have the same group, it's not necessary that you can map that O can be morphed onto P and that P can be morphed onto O. But if O is morphed onto P, then P will be morphed onto O. The second application we'll consider is that group theory can be used to prove the fundamental theorem of algebra, thus showing that looking at symmetries through group theory is very useful in general in many branches of mathematics.